Alrighty, welcome back to operating systems. So, after all the craziness of having multiple processes and children we can kill and orphans and all that fun stuff, we get a bit of a break today. So today should be fairly straightforward, give your brains a rest. A lot of you are working on lab 2, so that's good. So today's lecture will be hopefully fairly straightforward, unsurprising, and quick. So, there are two types of resources on your machine. They're broadly divided into preemptible and non-preemptible resource. So a preemptible resource is something that can be taken away and used for something else or otherwise shared. So, for example, your CPU is a preemptible resource. I can stop executing any process at any given time and give the CPU to another process, and then you are sharing the same. So that's talking about a single core. So typically when you are sharing something, if it's contended at all, I'm sure you've done this in your life, where you schedule it. So you each get a certain time period with whatever it is, and that's how you share it. So non-preemptible resources cannot be taken away without any acknowledgement. So an example of that, something like disk space. If a file takes up a gigabyte, you can't be like, I need to borrow 100 megabytes or something like that and I'll give it back later. That's not how files work, because that would probably overwrite the data. It would get messed up, you wouldn't be able to recover it. Another example would be memory. Right, physical memory. So as soon as you use it, you allocate it, and then whenever you're done with it, you have to tell the operating system, hey, I'm done with it. You can deallocate it. So there's an exception to this. So CPUs in like super high performance computing, where you have to actually reason about how your CPU works, you may be able to schedule a CPU like a non-preemptible resource. So you can say, hey, I need the CPU exclusively, and then you have it, and then you deallocate it when you're done with it. But that's only in like super sensitive high performance computing. We're just dealing with general computing, in which case we can share CPU cores easily. So there's two components. There is a dispatcher and a scheduler, and they work together. So the dispatcher is like the low level thing, and that is what is actually responsible for doing the context switching. So saving the registers of one process and then restoring another process to run, doing the context switch, that is the job of the dispatcher. The scheduler is like the high-level policy. So it decides what process to run and sometimes when. So the scheduling is what we're talking about today. So by default, the scheduler runs whenever a process changes state. For instance, a process terminates or something like that. So first, we will consider non-preemptible processes. That means they just run until they're done. Going back to like the unit programming approach. So once a process starts, it just runs until it's done. So in this case, if you are a scheduler, you only get to make a decision when a process terminates or if there are no processes currently running. So preemptive allows the operating system to run the scheduler at will. So if you run uname-v, you'll get a whole bunch of information about your kernel. One of the things it will tell you is preempt, and that means it uses a preemptive scheduler. So that's what one of the words means. So when we talk about scheduling, there are four main metrics. The first one is you want to minimize waiting time and response time. So those are fairly self-explanatory. Waiting time is just how long a process is waiting for the CPU. So how much time is that individual process idle, not actually executing. And then response time is how long does that process take from when it wants to start to when it first starts executing, and that is called the response time, because ideally, if it's something you interact with, you want that response time to be long. That process will not terminate, but you want it to be responsive, so you move your mouse and you instantly see it running, draws the updated mouse cursor on the screen, and then it feels like your computer's responsive instead of taking an entire second to run or something like that. The second job is it wants to maximize CPU utilization. So if you have multiple cores, It should utilize all the cores on your machine as much as it can. If you have a single CPU, it just means it doesn't want that CPU to be idle. You have to make a decision and make it quick. Then the next is you want to maximize throughput, so that's just completing as many processes as possible, which you might care about if you are just running like machine learning jobs or something that just takes a while. You don't care, you just want to get through them as fast as possible. And then the last thing, which is at odds with all the rest of them, is fairness. So you try to give each process approximately the same percentage of the CPU, and that way, it's not like you sharing, I don't know, something with your siblings. You want to be fair about it, and each one is treated fairly. Someone doesn't get like 99% and the other gets 1. So the most basic scheduling algorithm is one you have encountered every single day of your life if you've ever went to get food or anything else. So it is called first come, first serve. It's basically a line. So the rule behind this is the first process that arrives gets to execute the CPU, and the processes are stored in FIFO order, so first in, first out. It's just like a normal queue or a line we've had like every single day of our life pretty much, and it's based off the arrival order. So this is how we will illustrate our scheduling using a fun Gantt chart. So in this case, we want to schedule 4 processes. In this case, they're cleverly named P1, P2, P3, and P4. And then the other columns are arrival time, so that is at what time unit does the user request this process to actually start executing. And in this case, we're going to assume that they all want to start at time unit 0. Then burst time, you might think, hey, that's a weird term. Burst time just means how long each process wants to execute on the CPU for until it is completed. So process 1 needs to execute for 7 time units, process 2 for 4, process 3 for 1, process 4 for 4. And that's all we need to know about the processes. So they all arrive at the same time instant, so I'll just break the tie and tell you that the order they arrive at, like down to the nanosecond. And I say process 1 arrives, then 2, then 3, then 4. So if this was first come, first serve, well, at time 0, you have to pick which process to run. If we're just going off in line order, process 1 runs first. So it runs for 7 time units because we're doing non-preemptible first. So it just runs until it's completed. So it will take 7 time units to run. So at time 7, well, the scheduler has to make a new decision. What process do I want to run? And it is just the next one in the line. P2 runs for 4 time units. P3 runs for 1 time unit. And then P4 runs for the last 4 time units. And that's it. So any questions about that? Hopefully nice and boring as a change. So if we want to compute the average waiting time, well, for each process, we have to figure out how long each of those are waiting for. So process 1 is waiting for 0 time units because it wants to run at time unit 0, starts running immediately, its waiting time is 0. Process 2, well, it wanted to run at time equals to 0, and it started running when time was 7, so it was waiting around for 7 time units. Process 3 was waiting around for 11. Process 4 was waiting around for 12. So if you want to calculate the average, again, not terribly complicated. It is 0 plus 7 plus 11 plus 12 divided by 4. And that is 7.5. So the average waiting time for this case would be 7.5 time units. So we can do the exact same thing, except we'll assume a slightly different order. We'll assume it went P3, P2, P4, then P1. So if we do the same thing again, well, our schedule looks what we would probably expect. P3 was first, so it runs for its 1 time unit, then it terminates, it's done. Then based off the line, P2 runs for 4, then P4 runs for 4, and then P1 runs for 7. So if we were to calculate the average waiting time now, P3 waits around for 0, P2 waits around for 1, P4 waits around for 5, and then P1 waits around for 9. So 9 plus 5 plus 1 plus 0 divided by 4, that's 3.75. So just based off the order of these processes, our average waiting time was actually halved. So you might think that, hey, first come, first serve, we're kind of at the mercy of whatever order the processes arrive in, and we can probably do a bit better. So the astute among you would have noticed that, well, if I want to minimize average waiting time, I should probably just do the shortest job first. So instead of first come, first serve, we just always schedule the job with the shortest burst time first. And again, this is assuming no preemption. So if we do something like this, we will make it a bit more interesting by changing the arrival times. So only P1 arrives at time 0, and then P2 arrives at time 2, P3 arrives at time 4, and P4 arrives at time 5. Then otherwise, everything else is the same. So I always just write the arrival times on the top here. So I can see, when P1 arrives, when P2 arrives, when P3 arrives, and when P4 arrives. So if I was to do this schedule, well, at time 0, when I want to make a scheduling decision, P1 is the only process that wants to run, so the scheduler has no choice but to schedule process 1. So it gets scheduled, and again, we're in non-preemptible land, so it will run until it is done. So it will take 7 time units. So while it was executing, process 2, 3, and 4 wanted to execute, but the CPU is busy. Then whenever P1 finished at time equals 7, the scheduler gets to decide the next process to run. So if we're doing shortest job first, well, between P2, P3, and P4, P3, the burst time of 1 is the shortest, so it would schedule P3 to run. So P3 would run for 1 time unit, and then we have to make another decision. Do we run P2 or do we run P4? Both their burst times were 4, so it was a tie. So since there was a tie, to break this tie, we'll just pick whoever arrived first. We'll just go back to first come, first serve for any ties. So we would schedule P2 to run. It would run for 4 time units, finish at 12, and then P4 would run. So if we calculate the average waiting time now, hey, it's 4. Yay. So this all fairly boring so far, straightforward. Doesn't look like any questions. Nice change than like forking and then having a bunch of stuff. Yep.
How would the scheduler know each one how much time it is going to take?
Yeah, so you might notice this is completely unrealistic on a real machine because the scheduler would not know how long each process takes. So this is generally used after the fact to kind of judge other algorithms. So this is provably a way to minimize the average waiting time, but it's obviously not very realistic. Yeah.
Could we do sort of back-of-the-envelope calculation for finding the burst time by looking at how large the binaries of those processes are?
So so the question is, well, could I just guess the burst time by how big the binaries are? So you could guess, but as you might have figured out by now, your computer is very, very unpredictable. So you could throw AI in it and try and make better predictions of everything, but can be wrong, and generally with scheduling, there's no correct answer. It's just a bunch of trade-offs that we'll see. So today, so here's your point. This is not practical whatsoever. So provably, it will minimize average wait time, but we won't know the burst times ahead of time. You could use the past to predict the future, although might not be a good predictor. So you might, you might launch something at like 6 a.m., go, and then close it immediately, while other times if you have it at midnight, you know, you hack on it for like hours and hours, and you never know. And the other problem with this is something called starvation. So starvation means that a process might not actually ever get to execute. So in the case of shortest job first, if you just had a process that took a long time, and then you had a constant stream of very short jobs that come in, well, that long job would never ever run. And that is just, I don't know why we just use the term starvation for a process that might never run. Yep.
Whereas the other case, in the case that that long job does run, then it means that some smaller job that came after is not gonna run, so it's this or that.
Yeah. So the other thing, if you have a really long job, then nothing else can run too, right?
So some jobs can actually restart.
Yeah. Some jobs can restart, but the next thing we could do is something called shortest remaining time first. So we can add preemptions to it to kind of interrupt a long-running job so it doesn't just hog the CPU or something like that. So we can do a little tweak just to introduce preemptions. So we're going to just have the same idea as shortest job first, but we're going to tweak it a little bit and add preemptions. So the algorithm just becomes shortest remaining time first because we can interrupt processes and schedule a new one. So again, for all this, we're just assuming that our execution time is 1 time unit, so we can only interrupt on time unit boundaries just so we don't have to deal with fractions. So this also optimizes the average waiting time, and let's see what that does. So with the same processes, our schedule would now look like this. So at time 0, we still have process 1, which is the only process, so it would get scheduled. It would run for 2 time units, and then process 2 comes. So when process 2 comes, the scheduler can preempt and stop, pause, whatever you want to say, process 1. So at time 2, process 1 has executed for 2 time units. It wants to execute for a total of 7, so it has 5 remaining. So process 1 at this time has 5 remaining time units, and process 2, which just arrived, has 4 remaining time units. So if we're doing shortest remaining time first, process 2 is shorter than process 1, so we would schedule process 2. So we schedule process 2, it executes for 2 time units until process 3 comes in. So at this time instant, process 2 has 2 time units remaining because total of 4, it's run for 2 already. So process 2 has 2 time units remaining, and the new process 3 has 1 time unit remaining, so it is now the shortest. So we would interrupt process 2 and execute process 3. So it would run for its 1 time unit, and then it is finished. So when it is finished as well, process 4 comes in, which has 4 time units remaining. So we have 3 processes. Process 4 has 4 time units remaining, process 2 has 2 time units remaining, and process 1 has 5 time units remaining. So we'd schedule process 2 for 2 time units. Then at time 7, it's between process 4 and process 1. So we schedule process 4 that has 4 remaining. It executes for 4 time units, and then we finally finish off with process 1. Yep. So switching between processes is not intensive, you said? So switching between processes, remember we called context switching before? So we will keep track of the number of context switches that happen, because if the context switch takes like the same amount of time as each of these time units, then that's not good, right? We're wasting a lot of time. But if it's like a fraction of the time, then it's okay. Typically context switching accounts for like less than 1%. So, but we'll see later that, hey, if you context switch too much, that can be really bad. If I context every every 1 nanosecond, probably not good. Yeah.
That is also assuming that there's the way of knowing how much time
Yeah.
it takes, right?
Yeah, so this is also, again, assuming I know how long each process is going to take. Yep.
Yeah, so my question is if we don't know like how long the process is going to take, then what's the point of this?
Yeah, so this is mostly just to compare ourselves with other things. This is like the optimal thing to do if you just care about waiting time. But a lot of drawbacks, including you can't actually implement it.
So in practice, where would this go?
So in practice, you could use this to evaluate your scheduling algorithm if you wanted to. So this is just more theoretical. This is not super practical. But yeah, we can see with the same schedule, if we just do the waiting time calculation, well, our average waiting time actually goes down with preemptions, which makes sense. So the waiting time gets a bit hairier to calculate here because we have preemptions, but there is a fun little shortcut we can do. So, for instance, getting the waiting time for process 1, well, it's the amount of time it's waiting from when it wanted to start at time 0 to the very end. So I could just count every block where it's not executing. So like 1, 2, 3, 4, 5, 6, 7, 8, 9. That takes a long time. I don't want to count. So what you can do is you can calculate the time that process 1 was just around on the CPU in total. So process 1 ended at time 17, or sorry, at time 16 here, and it started at time 0. So the total amount of time it was on the CPU was 16 time units. And if I want to calculate the waiting time, well, if it was around for a total of 16, and I know its burst time was 7, I can just subtract. So 16 minus 7 means it must have been waiting around for 9 time units. So, whoops. So its waiting time would be 9, and you can do it for the rest of them to get the average waiting time of 3. All right, so first actual algorithm that can be used, round robin. So far, we haven't talked about fairness at all. And in fact, it's a trade-off with all the other metrics. So if you have something that has, the lowest average waiting time, which is the shortest remaining job first, or shortest remaining time first, then you're going to have the issue with starvation, and you're also going to have the issue where you can't implement it, and you're also going to have the issue where it is not fair. So the fairness thing to do is probably if you do have siblings and there was some toy that you and your siblings wanted to play with, you probably did something like round robin. So the operating system, like your parents would say, hey, you each get 30 minutes with it, and then after your 30, it's the next 30, and then you just kind of go around in a circle like that. So operating system does the same thing. So it divides execution into time slices. Sometimes literature wants to be fancy and call them quanta, and call the individual time slice a quantum. I'm not that fancy, but they use the terminology. I don't know why, but we can say time slices if we want. So what they do is it's just a queue again, but it's a queue that goes around and around. So you maintain a FIFO queue similar to first come, first serve, except that each process only executes for a certain time slice. So at the end of its time slice or end of its quantum, it gets re-added to the end of the queue. So it just goes to the back of the line. And then we just pick the next process at the front of the queue and go on and again. So what are some practical considerations for determining that time slice or quantum length? Yep.
If you make it too small, you're going to be wasting a bunch of time on context switching.
Yeah, if you make it way too small, you might be spending a lot of your time context switching. So if your time slice is like smaller than it takes to actually do a context switch, you're going to be wasting a lot of time. So what would be the opposite problem where my quantum length is gigantic? Yeah.
There are processes that are too fast that does not take the what's called time slice, the entire time slice is faster than that.
So a process can end early. So it can, if it doesn't use its whole time slice, it just terminates, and then the operating system can immediately schedule something else to run. Yeah.
But if every process like ends early, then there's no effect. Like if it's too big, then it would just be the same as
Yeah, so if the time slice is too big, it just becomes first come, first serve, right? Which kind of sucks. So if your quantum length is like 8 years or something like that, well, it's the same thing as first come, first serve, which kind of is not that great, as we saw at the beginning. So you have to be fairly careful about picking your quantum length or time slice. So let's do the same thing with a quantum length of 3 time units and see what fun this brings. So thankfully for us, this is about as complicated as it gets. Round robin's a real scheduling algorithm that also works, and these types of questions are easy things to put on exams, and they're not that hard, so they should be more or less free. So they do get a little tricky, so we'll see essentially as hard as they'll get. So here I wrote out, I have the same processes that I want to execute for the same amount of time, and I wrote the arrival time at the top again. So if I'm doing round robin, I will do a quantum length. Let me write. So we're saying our quantum length is 3 time units. So if our quantum length is 3 time units, well, at time 0, we only have process 1. So we can only pick process 1, and it gets up to 3 time units. Again, it can end early if it wants to, but in this case, it wants to run for 7, and that's less than 3. So P1 would execute for 3 time units. And when I do round robin, I find it much easier if you write the queue at the bottom. So at time 2, when process 2 came in, it would have been added to the queue and nothing else would have been in the queue, so process 2 is at the front of the queue. So at time 3, when process 1's time slice is done, well, my queue would look like this. So P2 would be at the front, and P1 gets thrown off at the end. So when the scheduler needs to make a decision what to run at time 3, should be fairly easy. It's whatever is at the front of the queue, which is process 2. So it gets scheduled for 3 time units because it wants to run for a total of 4. So at time 4, when process 3 came in, our queue would be process 1 would be at the front, then process 3 would be added to the end, and then at time 5, when P4 comes in, our queue would look like P1, P3, and then P4. Right? So at time 6, right here, when we need to make a new decision what to execute, what are we going to execute? Process 1, right? Straight off the front of the queue. Nothing. Unlike processes, this is not like something that will, hopefully something that will not wreck your brain. So process 1 would execute for another 3 time units because it can execute for up to 7. So it's still good. So my queue, whoops, I screwed up. Oh, sorry, I forgot to requeue process 2. So here, I did not requeue process 2, so it'd be P2, whoops, sorry. It would have been process 1, process 3, process 4, and then process 2, sorry. Process 2 would have been added to the end of the queue, and then we took process 1 off. So at this point, our queue would look like P3, P4, P2, and then P1 would be added to the back. So the next process we run is P3. It only runs, what are you doing, camera? All right, cool. All right, so P3 only runs for, yikes. Okay, that thing is dying. Okay, so P3 is done at that point. So P3 is done. The next process in the queue would be P4, P2, P1. So I would schedule P4 for 4 time units, or for 3 time units because it's my quantum length. And then at this point, my queue would be P2, P1, P4, and they all have 1 time unit remaining. So it would just be P2, then switch to P1, then switch to P4. So, any questions about that? Yep.
We had P1 was like did the slots, the one thing.
Yeah.
And then, but we didn't get P2 yet. And then so it's just P1. So P1 started another 3 slots.
Yeah.
We got P2 at let's say time 4.
Yeah.
Would P1 stop at 4 to give P2 the 3 slots, or would it continue 3 and then after 6 give P2?
Yeah, so the question is what would happen if we just had like, so P1 was still the same, that arrived at 0, and then P2 arrived at like time 4. So if that was the case, P3 would run for its 3 time slots, and then we'd have to make a scheduling decision at time 3, and it would just be P1, we have no other choice, and it would go for another 3 time units. It wouldn't get interrupted in the middle of it, even though it's like hogging it a bit. It still gets its time slice. So the only way that you get a shorter time slice is if you terminate. Yep.
So what if like 2 processes arrive at the same time? So which one would decide at the?
So if 2 processes arrive at the exact same time, you would be told how to break the tie. So, or you just pick one because it's a tie and it doesn't really matter. Yeah, lower process ID if nothing else. Yeah, so other things you would have to do is do some fun calculations. So like average, so average waiting time is something you would be asked to calculate. So you have to go through each process and calculate how long it was waiting for. So you can do the boring thing of like, oh, for process 1, how long was it waiting for? Well, 1, 2, 3, 4, 5, 6, 7, 8. And go and count how many times it was waiting until it finished. Or you could do something much faster. So process 4 ended here. Then process 1 ended at time 15. So the total amount of time process 1 was around 4. It was here, so it was around from 15 to 0, so it was around for 15 time units, and we know it was executing for 7 of those, so it must have been waiting for 8 of those time units. Then same thing for process 2. It ended here at 14. And it started at time 2. So it was hanging around for 12 time units, right? 14 minus 2. So it was hanging around for 12 time units. It executed for 4, so it must have been waiting around for 8. And that saves me a bunch of time. I don't have to count a bunch of stupid blocks. And if I do that for the other ones, process 3 was waiting around for, I can count this one, 1, 2, 3, 4, 5. So process 3 was waiting around for 5 time units, so that was 1, 2, 3, 4, 5. And then process 4, well, it ended at time 16. It started at time 5. So it was active for 11 time units. It ran for 4. So 11 minus 4, please say I can do math. It should be 7. So it was waiting around for 7. So if we do our average waiting time, there were 4 processes. And then this is something like 7. So the average waiting time in this case was 7. So if we do, I'll make it a different color. Orange, sure. If we do the average response, which is slightly different. Remember, response is the time from when it arrived to the time it first started executing. So for process 1, well, its response time was 0 time units because it started executing immediately. And why do we care about response time? So you might care about response time if this is an application you interact with. You want to see some response out of it as quickly as possible. The lower response time, the better. So for process 2, its response time was 1 time unit, so it arrived at time 2 and started executing at time 3. So it was waiting around for 1 time unit. For process 3, it got scheduled here at time, or it arrived at time 4 and didn't start executing till I believe this is 9. So its response time was 5 time units. And then for process 4, well, it's the same thing. It arrived at time 5 and then didn't start executing until time 10. So its response time was 5. So if we add those all up, divide 7, that should be our average response time, which is 2.75. And then the last thing you would be asked to do is tell me how many context switches there are. So how you do that is you don't count 0 as a context switch and you don't count termination as a context switch. So you just go through it and count however many times it switches between processes. So that erased it. So there's 1, it switched between process 1 to 2. Then there's another here, then another here, then here, then then not there. Then another here, here, and here. So if you want to count the number of context switches, you just count the number of red lines. So how many do I got there? 7. Yep. Yeah. Yeah. So when a process terminates and switches to another one, that still counts as a context switch. Although you can imagine it might be slightly faster because I wouldn't have to save the state of whatever's terminating, but I still have to load whatever I have to execute next. Yep.
So every time the complement is passed, it switches process, right?
So it doesn't have to. So in the case where like P2 didn't arrive to time 4, we would have gone back-to-back process 1, and that wouldn't have been a context switch. So context switch is only when we're switching between processes, not when the scheduler runs. Yep.
So then at time 10 over here, when P3 finishes,
Yep.
at time 12, P4 hasn't finished yet. Would it context switch because it's now time 12 and it's 3 things have passed?
No. So when P3 goes here, it gets 3 time units, and then it finishes early, it terminates, the quantum length resets for the next process. Yeah, it doesn't, you don't get, imagine someone could easily play that game if you knew the quantum length was, I don't know, say you knew it was 10, then, hey, I'll just make processes that only last for 9, or a multiple of 9, and then that thing the other processes just get 1 time unit all the time, get the spare every time, and I screw over every other process. So that's a reason why you could think of as restarting it every time. Okay, so fairly good so far. So the hard version is do it again, but quantum length is 1. Yeah.
Sorry, on the previous slide there was a note. It says on dies a new process or needs preemptive trigger the new one. Is that like a loop for every time?
Yeah, so we'll see a tie right now. Yeah. So this is like the hardest one it can do is the quantum length is 1, so we have to make a decision every single time, which gets kind of annoying. But thankfully, if you follow writing the queue at the bottom, it's not too bad. So at time 0, process 1 arrives, so it would be at the queue. I'll draw it for there. So process 1 would execute. Then after it's done its time slice of 1, it goes to the back of the queue. So it would go to the back of the queue, come again, and now we have this tie. So now there's a bit of a tie. So process 2 arrived at the same time we're throwing process 1 to the back. So the rule for this is always favor the newly arriving process. So we would favor process 2 and throw P1 behind it. And the idea behind this is, well, that's just newly arriving. I can lower my overall response time if I favor the newly arriving process over the old one that I'm just requeuing. So remember, for tie breaks, there's usually a reason behind them. So this one, favor the newly arrival process. Why? Because I want to minimize the average response time. So in this case, P2 would execute, then get thrown to the back of the queue. My queue would look like P1, P2, and they go back and forth. And again, I have the same situation where I'm requeuing P1 and P3 comes in. So I would favor P3 and my queue would look like this. So P2 would have been at the front, then P2 would have been behind it, and then P3 would have went to the very back. So now my queue looks like this. So then P2 executes, it is at the front of the list, and now we have that same situation again. So my current queue before would look like P3, P1, and now P2 is being requeued and P4 is arriving. So I would favor P4 and then put P2 way at the back. So now the hard part is mostly done. So at this point, I just go through round robin with all these processes. So thankfully, when I schedule P3, P3 only wants to execute for 1 time unit. So it gets scheduled and it's done. And now my queue looks like P1, P4, and P2. So it's just going to ping pong between all these processes over and over again until they are done in that order. So hopefully I can go fairly fast. So it would go P1, P4, P2, P1, P4, P2. And now at this point, P2 is done because it wants to execute for 4 time units. And we are now at 4. 1, 2, 3, 4. So P2 is now done. So now my queue would look like P1, P4. So then it would just go P1, P4, P1, now P1's done, then P4, now P4's done. So any questions for that? That's as hard as it gets. Yep.
Why don't we prioritize D3 when it came instead of D2 so that if you want to optimize response time?
So the reason we didn't immediately execute P3 is because P2 was already in line before it even arrived. So it can't butt ahead of it too bad. So you could tweak it if you really want to optimize response time, go the immediate front, but then you might get into fairness things, right? So if that always happened, then if you just have a bunch of really short processes that finish at a quantum length, they'll always run immediately, and that might not be good. Yep.
What if there's a mix of preemptible and non-preemptible processes?
So typically, there will not be a mix of them. It's an either-or thing. Either I schedule it non-preemptible or preemptible, and you don't really go back and forth. All right, so then the fun calculations start. So average weighting. Well, we can, again, figure out when things end. So this is when P4 ends. 15 is when P1 ends. 14, 13, 12 is when P2 ends. and P3 is not too hard to figure out. So my average waiting time for process 1, well, it was waiting around, it finished at time 15 and it arrived at time 0, so it was there for a total of 15 time units, executed for 7, so it must have been waiting for 8. Process 2, it ended at time 12, it arrived at time 2, so it was around for 10 time units, executed for 4 of those, so it must have been waiting around for 6. Process 3, we can see here, only waited around for 1 time unit. And then process 4 ended at time 16, arrived at 5, so it was there for a total of 11, and it took 4, so it must have been waiting around for 7. So if we calculate this, 5.5, so our average waiting time went down compared to our quantum length of 3. Next thing is response. So the average response, well, process 1 ran immediately, so did process 2. Process 3 only waited for 1 single time unit, and then process 4 was the longest one, and it waited for here for 2 time units. So we can see that the response time went way, way, way down, which is great. Bad thing. How many context switches did we have? How many was that? 14. So the number of context switches was 14. So that may or may not be a bad thing depending on how long a context switch takes. So everything's kind of a trade-off. So if you wanted to practice, hey, you can do it again, quantum length 10. Now it's first come, first serve, right? Because 10 is longer than the longest process, which is only 7. So you could go ahead, calculate it if you want. Only 3 context switches now. The waiting time happened to go down, but the average response time got real bad. So this is basically summarizing what we discussed. You don't want a quantum length that's too short, and you don't want one that's too long. And if you simulate round robin a bunch of times, it generally has a bad average waiting time when the jobs are of similar length. So scheduling just involves a bunch of trade-offs. We'll see other things we can do next lecture. You can combine things, do all sorts of weird things, but round robin is like a good, safe scheduling algorithm that's super easy to implement and works relatively well as long as you pick a good time slice. So we saw first come, first serve, shortest job first, added preemptions, shortest remaining time. Saw it optimized waiting time, wasn't realistic. Saw round robin, fair, something you could implement. Yay. All right, we're good. All right, so just remember, pulling for you. We're on this